Right, gents. Welcome to week 2 of electrical and electronic power and drive systems. What we're going to do this week, 3 general areas. We're going to have, first of all, have a look at the principles of a 3-phase induction motor. Next week, we'll turn that into speed, one method of speed control of that motor. And the presentation analysis is along the lines of what you need to do for the first assignment, which I'll be issuing next week. Then after that, we're going to have a look at power flow in terms of complex power flow. So it's building on what we did last week. We're going to be doing some complex number arithmetic with both polar and rectangular complex numbers as appropriate, and I'll do a brief revision of how that all works. And then we're going to have a look at power factor, the subject of power factor correction. So we talked last week about power factor being something, or poor power factor being something supply authority will penalise you before, and therefore we need some method to correct poor power factor. So we'll do a little bit of talking around that. Okay. We'll see how far we get with that, and if need be, we'll pick up with where we left off next week. All right. So, 3-phase induction motors. They are the motors most frequently found for general applications in industry. They're simple, rugged in construction, low-priced, and relatively easy to maintain. They run essentially at a constant speed for normal loads, and for a given load they will run at a constant speed. Their speed will tend to change with load, and you'll see why shortly, but within their normal load range for their size, they'll give you a fairly constant speed. Speed control is relatively simple, using the modern inverter drives, variable speed drives that we're going to take a brief look at next week. And the motors consist of 2 main parts. A stator that is a system of windings, and we'll talk about what that does in the way of creating a magnetic field as we go through this session. And the rotor, which is the bit that turns, and that is a construction made out of laminated iron and conducting bars. Okay, again, we'll look at that in more detail as we go on. The best way to look at how to get across how a squirrel cage motor actually works is to imagine the cage part of it as though it's rolled out flat like a ladder. Yeah, so it's called a squirrel cage rotor, and when we look at the actual rotor construction, you'll see why that's called that. Okay, but if we've got a series of conductors like these conductors here, they have length L in this ladder. They're like the rungs of the ladder, but they're short-circuited by these bars top and bottom, so they form conducting loops themselves. Yeah, and that's the bars A and B, that one there and that one there. If we take a permanent magnet like the one we've got sitting in this diagram, and we move it rapidly over the bars at speed V there, so that a magnetic field here, B, sweeps across these conducting bars. So what we've effectively got is we've got a conductor that we are going to move a magnetic field. So here's our magnet with field going north to south. We're going to move that across that conducting bar. Now, from basic science, you should know that if a conductor experiences a change in magnetic field, i.e. a magnetic field cutting across it, you will induce a voltage across the ends, and then because the ends of that conductor or a complete circuit will end up with a current. So by pulling that magnet across those bars there, we're going to induce a voltage in each conductor while it is being cut by the flux. That voltage would be according to basically that formula: the flux density times the length of conductor in the field times the velocity it's being moved. Okay? So that's what we do. In doing that, because what will happen here, just extend this page, let's have a look at this. If we look at this conductor, we've induced a current in it. Let's say we've got a current going into the board. That would mean that we'd get a field around that conductor that's got some direction like so. We've then got our field from the magnet, north-south, that will not, one of the properties of magnetic field, magnetic lines of force, is they won't cross each other. So what will happen is, this field from north to south here will go round that conductor to get between the two poles and effectively force it or pull it in that direction if it's free to move. So we end up, by moving that magnet across there at speed, we end up having a force on these conductors in that direction. Force. Yeah? Just by moving a magnetic field. So the induced voltage immediately produces a current I, which flows down the conductor under the pole face, through the end bars and back through the other conductors. So we get this circular current around these conducting bars inside the motor. Yep. However, there are complications to that. Because the current carrying conductor lies in the magnetic field of the permanent magnet, it experiences a mechanical force. That force is called the Lorentz force. Yeah, Lorentz force. Not really sure exactly how you pronounce that name, but it looks like Lorentz to me. The force always acts in a direction to drag the conductor along with the magnetic field. That's always going to go with the field. So if we pull the magnet that way, the force is going to go in that direction. We will pull it from right to left, it will go in the right to left direction. So in this case, if free to move, the conductor bars would follow the magnetic field to the right. All okay with that so far? Yep. Now, however, as the ladder of conductors picks up speed, so we've moved this magnet at a certain speed, initially the conducting bars are stationary. And remember, there has to be a difference. It has to be cutting across that conductor to induce a current in it. Alright? So as the ladder picks up speed, the field will be cutting across the conductor less rapidly. Because the difference between the two, as this one's gone like that, and then suddenly this one starts to move, the difference between the two has become less. Yeah? Consequently, that'll mean the force on the conductor will decrease, because it's reliant upon the difference between the speed of the magnetic field and the speed that the conductors of the rotor are moving. So, because if the ladder and the magnetic field were moving at the same speed, it wouldn't be cutting across and you'd lose the current in the conductors. Do you all get that? Do you get that, Danny? If they were moving, if the magnetic field and the conductor were moving at the same speed, you wouldn't have the field cutting across the conductor, and therefore you'd had no induction. So you wouldn't get the currents flowing in here. They would disappear because there's no relative difference in speed between that moving and this moving. If they move at the same speed, you lose the current in there, and effectively the force would disappear, and the ladder or the rotor would stop moving. Okay, what that means is there's always a difference between the speed the field moves and the speed that the conductor's bars move at, and we'll come back to that again shortly. Yeah, so we created the speed of a magnetic field. The speed of the rotor is always going to be slightly behind that. Yeah, otherwise you wouldn't have any force. Okay. The actual rotor is like that ladder rolled up. So it looks like a cage that you'd have a squirrel run inside in its little hutch, pen, whatever you might put a tame squirrel in. Yeah. So it's like a little hamster's cage, but I don't know why they decided to call it a squirrel cage. In a real motor, the moving permanent magnet from our initial analysis of this, it's not a moving permanent magnet. It's in a three-phase, it's replaced by a rotating magnetic field. So the rotating magnetic field is produced by three-phase currents that flow in the stator windings. So we use three-phase system that have got voltages that peak at different times in the rotating cycle to effectively create a magnetic field that goes around the stator and pulls this cage around. So the field itself doesn't move, but effectively you recreate a rotating magnetic field. And I'm now going to attempt to explain exactly how that works. Are you all okay with that? Yeah. If we consider a rotor with what's called 6 salient poles, each with a coil of 5 turns, coils that are diametrically opposite are connected in series by 3 jumpers, A to A, B to B, and C to C. So what effectively happens magnetically is, with the currents in the right direction, we create north-south poles that are opposite each other. Yep, 3 of them. 3 pairs. 6 actual poles, 3 pairs. Okay. This creates 3 identical sets of windings, A to neutral. If you look at these ends, they're all connected to each other. A to neutral, B to neutral, and C to neutral. Yep. The 2 coils in each winding produce magnetomotive forces, a field, that act in the same direction. All right? So we get a field in there. What that then does is, if we take the 3-phase supply, 3-phase mains is effectively 3 sine waves 180 degrees apart. So they peak, 120 degrees apart. These peaks are all 120 degrees apart from each other. I make no excuses for using the old colours. They are the most visible on the board. Red, yellow, blue. They know black, grey and brown. Yeah, brown, black and grey. I don't know what the order is, but that's not so easy to distinguish on. What I don't like is black is the new blue and blue is the new black. But there you go. Somebody in Europe decided that would be a good idea. So we got these 3 phases that peak at different times. So if you look at these little diagrams here, we've got the field effectively being created in different direction as we move along one cycle of 360 degrees. Yeah, and I've got on the next couple of 3 pages, I've got these drawn much bigger so you can see what's going on with the field in the motor. Right. So if we take the flux pattern at position 1, it's got the flux going through the rotor and us in that vertical position there. Is the basic direction of that field. As we go as we go round to the second position, our field, because it's now the A winding that's fully energized, we've got a field in that direction. So it's pulled the rotor around by 60 degrees. Yep. So it's effectively creating a field that's not being physically moved by moving the magnets, but it's been moved or changed by the fact that this sine wave is pulling it round the rotor. Yep. And then in position 3, we've got a field acting in that direction, so it's pulled the motor around another 60 degrees. In total it's moved 120 degrees. Like so. Yep, 120 in total, sorry. And if we look at that, position 3, we've gone from 0 to 120 degrees. In the 4th position, our rotor, if we put the arrow on it, it's pointing downwards. We've effectively moved through 180 degrees. That's where we are on the sine wave. Okay. And lastly, position 5 and 6. Position 5, we're in that direction. We've moved through 240 degrees. And then here, we're in that position. 0.6, we've moved a total of 300 degrees. And then the last position at 360 would have us back up the top here. Can't remember if I put that one on. No, I haven't. But we'd be back up, pointing back where we were. So in one complete cycle of the 3-phase sine wave, we've created a magnetic field that's pulled the rotor around a full 360 degrees. Yeah. Just by the fact that we've got our system is designed so we've got 3 phases of electricity, 120 degrees out of phase with each other. Yeah. All both okay with that so far? Cool. Good. Right. Synchronous speed of induction motors. Because a rotating field that turns the rotor in an induction motor is created by 3 sinusoidal currents at a particular frequency, the speed that the rotor rotates will hence be directly proportional to the frequency of the supply. So a motor on 50 Hertz will run slower than one on a 60 Hertz or 100 Hertz or whatever. And that's the general principle of the motor inverter that we'll talk about next week, is that we use electronics to vary the frequency. Also, it's impossible to increase the number of pole pairs around the stator. This has the effect of reducing the angle between each pole and hence directly affecting the synchronous speed of the motor. So, in a two-pole motor, i.e. where each phase has one pair of poles associated with it, so we got the red phase top and bottom, then the yellow phase and the blue phase. There's 120 degrees between phases. So we've got 120 degrees there between red and yellow. We've got 120 degrees between blue and red. And we've got 120 degrees between yellow and blue, effectively. Yeah. If we add a set of pole halves, a set of poles between those, so we got two pole pairs per phase. Yeah, we end up with an angle between poles of 60 degrees. Hence, for every one cycle of the mains, we're going to only move 180 degrees from red to red instead of 360. Yeah, so we're effectively going to halve the synchronous speed by making it a 4-pole motor instead of 2-pole. You got that? Yeah. So, the synchronous speed of an induction motor can be calculated from N synchronous, little n synchronous, is 60 times the frequency over P. Alright, because the 60 comes from, we want the speed in RPM. Yeah, F is the frequency in Hertz, and that's cycles per second, and P is the number of pole pairs we have for each phase. Yeah, so if we look for a 50 Hertz supply, synchronous speed, 50 times 60, over the one pair of poles per phase gives us a synchronous speed of 3000 RPM. If we do a 2-pole motor, 50 times 60 over 2, 1500 RPM. So that kind of calculation, fairly simple, and most motors will have that synchronous speed marked upon them anyway. Yep. Slip. Right. So we're coming back to this situation of the difference in speed between the moving field and the speed of the rotor. As discussed previously, the field in the rotor is created by voltage induced in the rotor bars by the change in rotating magnetic field. If the rotor was to turn at synchronous speed, the rotating field would no longer cut the rotor bars, no voltage would be induced to create the rotor field, and hence the torque would be zero. The motor would stop. Yeah. So there has to be this relative difference between the speed of the magnetic field going round and the speed of the rotor inside it. Otherwise, it don't work. Yeah. For these reasons, the induction motor never turns at synchronous speed. It's always a little behind. The difference between synchronous speed, Ns, and the rotor speed, Nr, is called the slip speed, or just slip. So the slip speed is the synchronous speed, take away the actual rotor speed of the motor. Often, it's more often expressed as a ratio called the fractional slip, which is the synchronous speed, take away the actual speed, so the slip over the synchronous speed of the motor. Or we can do it as a percentage slip, which is that times 100. Yeah. So that's effectively the percentage of the actual speed of the motor you lose due to slip. Right? Yep. Right, Danny? Starting characteristics of a three-phase induction motor. Consider the motor with a locked rotor. So we bolt the rotor so it can't move. Okay. If we do that, the relative speed between the moving magnetic field and the rotor speed will be at its highest because we're not letting the rotor move. Therefore, the bars are being cut as fast as they could ever be with this magnetic field. The difference between the magnetic field moving speed and the rotor speed is as big as it's ever going to be because the rotor is locked. The rotor bar will generate an EMF, and hence the motor current will be very high, several hundred amps typically. Yep. So you're going to get a really high voltage, really high current flowing in a rotor if you lock the rotor. Yep. The force and hence the torque exerted on the rotor will be very high under those conditions. If we then release the rotor will rapidly accelerate in the direction of the rotating field. As the relative speed difference between the stator field and the rotor field is reduced progressively. Yeah. As that happens, the motor will accelerate until the torque being produced is equal to the braking torque of the loads applied and the frictional forces that are apparent in the motor. So when you get an equilibrium between the forces due to the torque of the motor rotating and the forces of friction and load on the motor will sit at that stationary or equilibrium speed. Yeah. At no load, the percentage slip is small, usually less than 0.1% of synchronous speed. Consider a motor running initially at no load speed. When a load is applied to the shaft, okay, the motor will begin to slow down. The effect of that will be to increase the difference in speed between the rotor bar speed and the rotating magnetic field speed, which in turn would increase the rotor bar current progressively, which will increase the motor torque. The motor will not slow to a halt. The motor torque and braking torque from the load will reach a new state of equilibrium at which the motor will then turn at a new constant speed. So we've loaded the motor up and it will self-create more torque to find another equilibrium speed slightly lower than it was due to the change in speed between magnetic field and the rotor speed. Yeah. So almost you could say it's almost self-regulating in that sense. Under normal loads, induction motors run very close to synchronous speed. For large motors, 1000 kilowatt or more, at full load the slip rarely exceeds 0.5% of synchronous speed. For smaller motors less than 10 kilowatts, at full load the slip seldom exceeds 5% of synchronous speed. This is why induction motors are considered to be constant speed machines. Yeah. However, because they never actually turn at synchronous speed, they are sometimes known as asynchronous machines. Yeah. Torque and speed characteristics of this type of motor. Torque of motor is dependent upon speed but cannot be expressed by a simple equation. Preferred way to show this relationship is in the form of a curve. The curve below is a typical torque speed curve for a motor whose nominal full load torque is T. So here, along this line, is the nominal full load torque T. And that's along a line of 1 times that full load torque T. Yep. And this is the curve according to its percentage of synchronous speed. The starting torque for this type of motor is 1.5 times the nominal torque. And there's something called the maximum torque, which is called the breakdown torque, at around 2.5 times T. The pull-up, what's called the pull-up torque, is the minimum torque developed whilst the motor is accelerating from rest to breakdown torque. And that's shown on the diagram there. At full load speed, there, which is this, where these two lines meet, the line of 1T meets the curve, its speed N runs at that speed under full load, and that would be specified for the motor. If the mechanical load increases slightly, the speed will drop until the motor torque is again equal to the load torque. As soon as these are equal, the motor runs at a constant but slightly slower speed. If the load torque exceeds 2.5 times T, the breakdown torque, the motor will quickly stop. Small motors, 15 horsepower or less, develop breakdown torque at a speed ND of about 80% of synchronous speed. Big motors, 1500 horsepower or more, attain breakdown torque at about 98% of synchronous speed. 1500 horse is a hefty motor. It's a big motor, that is. Alright? So this gives you an idea of the sort of level we're studying the characteristics of a particular type of motor too. Yeah? Alright, with that, are you both okay with what we covered there on synchronous motors and how they work? Yeah? So that's the principle behind them. And when you do the assignment, you may well be asked to look at some other motors. That's the type of thing you're going to be expecting you to look at so that you can analyse their suitability for a given application perhaps. Alright?